Let's talk about electromagnetic induction. Firstly, who's Faraday? And why does he have a law? Well, long story short, there's this guy, really smart guy, who discovered that there's this thing called induced EMF if you have a change in flux, a magnetic flux. So that equation is the main backbone for this whole idea of electromagnetic induction. So you can write out that the induced EMF, we call it induced because induction, induced, there's no battery providing the current, it's just gonna appear. So we can say that this is the induced EMF. Okay, and that, what is this fish symbol? This thing is called proportionality. Means for a linear change, let's say if this becomes 2 times bigger, this one also 2 times bigger. That's what it means by proportional. So induced EMF is proportional. And what should we add there? Proportional to the rate of change. What is rate of change? There you see d something dt. d phi dt. When there's a d by d something, there's a rate of change of what is changing. We call this magnetic flux linkage. In a little bit, the diagram down there will see what this magnetic flux linkage is. Okay, so anyway, this one is 2 marks. M1 for talking about proportional to the rate of change, EMF proportional rate to rate, then of change of magnetic flux linkage. Magnetic flux linkage is linkage is an optional word. Magnetic is also optional. So you talk about change of flux, that's fine. But if you want to be safe, just in case the mark scheme gives a mark for flux linkage, throw it in. Why not? Alright, let's see. So we have a solenoid, a small coil, and one on the end. So this thing is what we call a solenoid. You wind round and round and round and round, and you have a tiny little coil also here. Why got 2 coil? When there's 2 coil, one create the changing field, the other one experience the changing field and have an induced EMF or current, or both. So it tells a bunch of information. Coil has cross-section, diameter, 63 turns of wire. That's a lot. I guess the diagram is not to scale, so we can't really see the 63 turns inside here. But anyway, the solenoid produces a magnetic field in the region of coil C. So very nicely, they gave us the equation here. And that means, okay, so we have a changing field, changing flux that we can create. This one, because you send current through the wire like that, here's some kind of current. I zoomed in a little so we can see it bigger. The currents, when at first if there's no flux, this coil, let's say the flux through this tiny little coil is 0. So flux initial 0. But once you have current, like this orange one here, going through the coil, like this, for example, zoom, 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 over here, you will have some kind of flux. Use your right hand grip rule. Which direction is it? I think this side. Okay, anyway, your right hand grip rule, and you will find that there is a magnetic field generated that kind of kind of looks like this if I draw the flux lines. So inside the field should be about approximately parallel, all the flux lines. But once you come out, then they will start to spread out and loop around. So this is the magnetic field of a solenoid. So this one is pointing this way. Whoa! Suddenly there is flux through the coil on the right. Look at that. So from 0 flux, now you have, oh, my head's blocking it, some flux. Of course, you can calculate it if you know the values. But the whole idea is there is a change. At first, nothing. In the beginning, there was nothing. Suddenly, there is flux through this coil, and the coil does not like it. So to oppose that change, this coil will try to do its own current to create its own magnetic field to oppose the change. So for example, maybe it says, I do not like this field that points to the left, so I'm going to create my own field that points to the right. I can do that by generating some kind of current in my coil. Or maybe, let's see, this one should be right hand grip rule pointing downwards. Okay, so that maybe looks like this. So current will be there such that you create your own field to oppose the change, so pointing to the right. That's just an example of what it means induced EMF. So now there can be, depending on what you connect at the end, if you connect an ammeter, you would measure a current flowing inside this tiny coil. Just because of a change in magnetic field, which are these purple lines. All right, so let's move on. There is going to be a change, and they give us a nice graph. Look at this. Nice graph to show how current is changing. So you look at this. Current is going to be changing up and down, alternating. And that means that the magnetic field or the flux density will also be changing up and down, up and down, up and down. So there's a change in flux. Now reminder, what is B again? Let's go back to this one. B is defined as the magnetic flux density in the coil C. So I'm going to clear up the diagram a bit. B is right there. Okay, I think we are good to go. So what are we supposed to do with this thing? State 2 times where there is no electromotive force induced in coil C. So when is there going to be electromotive force? Let's think back about our Faraday's law. Faraday's law tells us that the induced EMF is proportional to the rate of change of flux. And we don't have a graph of flux, but we do have a graph of current. So who generated this current? Or what does this current do? So we're going to say that this current generates a B field. And the B field is calculated by flux. So number 1 generates B field. Number 2, flux we measure by B times A. So they are all linked together. You can say that, well, since flux is proportional to B, you could change this equation and say EMF is proportional to dB dt. Sure, we can say that. Or we can also say, hey, since B is proportional to I, since that's given to us here, B proportional to I. From this fancy equation, that's all. So we can say that, all right, we change our equation a little bit and we go last round. Induced EMF is proportional to, we replace the B with I, so di dt of the solenoid. So where is EMF 0? When EMF is 0, that's when we say the rate of change of current is 0. This is also known, by the way, if you see di dt, this is referring to the gradient of your IT graph. So you have an IT graph here, right? This whole thing is referring to the gradient of it. So let's look at the gradient. Where is the gradient 0? Look carefully. Gradient 0 means the graph is flat, or a more proper term is it is turning. So up here, I just draw one point. This is where your gradient is 0. So gradient 0, also known as di dt 0, which also means that at this point, the EMF is 0. And right here, EMF is 0. They're all related, thanks to Faraday's law, which is right here, this one. So that's one possible place where you can have no electromotive force. Where else is gradient 0? Down here, there's one more. Up here, there's one more. Down here, there's one more. All these are places with 0 EMF, 0 EMF, 0 EMF. The main idea is make sure you know how to think through Faraday's law in terms of graphs. So I can pick 2 points, any one I want, as long as it's like T1 or T3 or T5 or T7. Let's write down T5, T7, all also okay. So there's just one mark for you to know how to interpret this graph. Moving on. Induced EMF, find 2 times where the induced EMF is maximum but opposite polarities. Maximum EMF. Okay, so now we have to change our thought process a bit. When induced EMF is maximum, that means the di dt, which is the gradient, must also be maximum. Where is gradient maximum? Let's use green color for this. Maximum. So there's one possible place here. This is where the steepest part of the graph occurs. I'll try to draw again. This one is going to be a negative gradient, right? Negative. This side is also where the steepest occurs. This side is a positive gradient. Then we have negative gradient, positive, negative. The rest are off the graph, so there's 3 possible answers here. So which one shall we choose? Be careful, they say maximum but with opposite polarities. Means if this one is negative, then you choose a positive one lah, opposite polarities. So different gradient, different EMF, one positive, one negative. So I'm going to choose T2 and T4. You could also choose T4 and T6 because they're opposite, but I'm just going to choose the first one. So this is A1. Now, the final bit of the question, this one. Oh, so tricky, so tricky. The alternating current in the solenoid, at first was AC, right? We connect the AC. So we go to your diagram, you could actually draw an AC up here, AC power supply, which the symbol kind of looks like this. Plus minus, alternating. But now you're replacing that with something else. What do you replace it off? You replaced it with a constant current. Constant current is DC. DC can generate change in flux, man? Can. DC current of 5 amps. So this is our current flowing through the coil at the moment. Now, if you just kept it at 5 amps steady, no change in flux, but you did something. So calculate the average EMF when the current is reverse. So this is going to cause a change in flux. Although it's DC, yes, but there will be a change in flux because you reverse over a certain time. So you want to find average EMF. Okay, so we start off with equation first. What's Faraday's law? E equals to... There's a negative, but it doesn't really matter here. You just find the absolute value. So I'm going to ignore the negative. I'll put it here. There's a negative, yes. D phi dt. But since you cannot find the exact gradient, you want to find average, right? Whenever you see the word average EMF, then you can use delta phi, delta t for actual calculations by plugging in values. But don't forget, we're looking for induced EMF in coil C, so the tiny one. So that means there's many turns, 63 turns, so we must include a N phi, magnetic flux linkage, N phi, because there are many turns. Right? So what do we plug in? We know N, we know T, phi. Phi is the tricky one that a lot of people get stuck. So what do you plug in for phi? Let's look at this diagram of 3 cases down here. Let's say you have a current moving forward at 5 amps. Maybe in this direction, 5 amps. Sure. Then that will cause a field to be generated in this direction, cutting through the coil C, something like that. There we go. So there's a change in flux. I mean, there is a flux pointing to the left when you have a 5 amps. But you need to reverse the current. So in order to do that, you gotta remember that you need to reach 0 first, mark. Because you see, if I have current, current, I am 5 amps DC. Then I want to go to negative 5. So of course I have to change like that. Over a certain time, I don't know, average. It could be a straight line, it could be a curve, who knows. But the point is, you need to pass by 0 current. So that means at one point in time, there will be no current in this coil at all. So there's no flux. No flux. No B. Nothing. Okay. And then later, when you have reversed already, now your current is the other way. 5 amps. And this will be going... How do I draw this? Down. Oh, down, 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 down. And you have a field of pointing to the right now. Like this. I draw the lines roughly like that lah, okay. So you see the flux change direction already. So now the flux is back to beginning, but now reverse the other way. So if you want to calculate change in flux to plug inside here, you need to know what is the B and how it is changing. Okay, so let's expand this a bit. This one will be your N times delta BA delta T. B is changing. Area is not changing, right? You didn't change the shape of the coil, no. Area is still the same. So this one will just be, you can take it out of the delta. So this will be NA times delta B. You could go a further step and talk about delta I lah, but it's okay. We'll do this. So if you can find delta B, you can solve this problem. What's the change in flux from number 1 forward 5 amps to number 3 backwards 5 amps? Reverse, be very careful. So if you can use your calculation, the equation they gave earlier to find the change in B, So the magnetic field here at this moment in time is going to be, what is it? 9.4 times 10 negative 4 times current, which is 5 amps. This will give me a value of about 4.7 times 10 negative 3. So I'm going to write that down. 4.7 times 10 negative 3. This is B. Okay, why do I write the A there? 4.7 times 10 negative 3. Okay, so that is at this state, B1. B2, don't have, right? 0. So in this case, if you want to find the change in flux from number 1 to number 2, this one, your change in B that you need to know is 4.7 times 10 negative 3 minus 0. Or I guess final minus initial. Okay, 0 minus. Okay. We follow convention. Final minus initial. 4.7 times 10 negative 3. So this will give me a decrease in magnetic flux density. Negative just tells me it's decrease. So if you just plug this inside your equation up there, it's not complete. You're only changing it halfway from some flux to no flux. But there's one more change. This one, still 5 amps, but in the opposite direction. So maybe to represent that, I'm going to use a negative sign. And so I will write B3 equals to 9.4 times 10 negative 4, but negative 5. Just to remind myself, oh, now the current is reversed already. So this one is still 4.7 times 10 negative 3 Teslas. Sure, let's put a unit. But there's a negative sign here. So if I want to find the change in flux from here to here, change in B, this will be negative 4.7 times 10 negative 3 minus 0. What? So there is another change, which is negative 4.7 times 10 negative 3. Same amount. So you remember this, if you are talking about reversing the flux, this is called the reverse. There's actually two times of the 4.7 happening here. From forward to no flux and no flux to backward flux. This change is 4.7. Hey, my head is blocking. Okay, this change is 4.7 here. And the other change here is also 4.7. So it's a times 2. So I write there, up here times 2. So that is our total change in B. So let's finally do our calculation. This diagram hopefully helps you to think of reverse flux. Whenever there's a reversal, it's actually a times 2 because it's 2 times the change. Forward to backward. Forward to nothing, nothing to backward. Let's plug in our values. Okay. Right. So number of turns here is 63, and that is the tiny little coil. Okay, so that's given to us. Area. What is area? Let's go back to the diagram. They didn't give area, but they did give us a cross-section diameter. Aha. They gave us diameter. I'm going to use a radius is our D. So area, cross-section area of this cylinder, or I should say the area where the flux passed through. This one can be pi r squared. So I must remember to plug this divided by half lah. Okay. So pi d over 2 squared. Gotta remember to do that. Sub that in. Okay, let's do this. What is the half? Half of this is 1.8 times 10 negative 2. That's our radius. So plug in 1.8 times 10 negative 2 inside our answer. Let's do the calculation. Okay, almost there. Let's go. So this one will be pi times pi r squared. R is 1.8 times 10 to the negative 2 square. Right, that is my radius. Now the delta B, this one will be change in field. So 4.7 times 10 negative 3. And it's reverse forward to backward, so only times 2. Divide by time. This is 6 milliseconds, so 6 times 10 negative 3 seconds. If all goes well, I should get 0.10046, something like that. Final answer, I'm going to keep it to 2SF, so I'm going to put 0.10. Please be very careful for your 2SF. Because your answer given is mostly 2SF, so Cannot have one SF, either 2 or more. 2 SF to 3 SF is okay. But be very careful. Okay, this one is going to be a 3-mark question. One for final mark. Down here. One for... Where is my... equation here. N d phi dt. Faraday's law. That is C1 mark. And lastly, if you sub the correct numbers into your thing, there's a C1 for substitution of correct values into the equation. Alright, so that's all for this question. Some of you may have used slightly different methods. Maybe you went a step further and say, Miss, delta B is related to the delta I, right? Okay, so you can sub in your equation. What is the number? 9.4 times 10 negative 4. Sure. So this will be Na times 9.4 times 10 negative 4 times your delta I instead, which is 10 amps. Sure. 5 minus 5, 10. Can also lah. But this is the thing of being reversed. So be very careful when you see the word reverse field inside the past year question. It's kind of like AC lah. You forward, then you backwards. So reverse. So the whole change, the total change is 2 times. From here to here and here to here, 2 times the change in current. Okay, so if this is delta I, this is delta I, total change is 2 delta I. Same thing for flux. Okay, so that's all for this question. I will see you in the next one of induction or something else. Bye bye.